Many thanks for the kind introduction as well for the invitation. So the talk I will give you today is about transient multiphase flow phenomena, the reversible pump turbine, and the effects on structural integrity. So I will start shortly with a context. Hydropower and more specifically hydraulic machines today are going through a profound modernization need. That is mainly a result, of course, of energy transition needs, integration of competitiveness and security of energy supply, as well as resilience against climate change. Hydraulic machinery and more broadly, so hydropower plants, so we know were designed back in the centuries. Many of them are still in operations, being there since more than 50 years. And their design were mainly done around a single optimal point and the given range around it, where all optimizations and efforts were mainly addressing this search for best efficiency. With this paradigm shift that hydropower is going through nowadays, mainly because, as I said, of the energy transition requiring broader flexible operations, as well as resilience to climate change, which ask, for instance, to operate in more extreme and unconventional operating conditions, such as minimum or maximum water level or sediments-rich environments, that requires today hydropower to operate towards multiple operating points. These ask for new operational requirements, namely extended operating range, more frequent transient operations. So we hear more and more those high numbers of startup and stop per day, efficient water management, as well as I already said, extreme operational environment. All those new requirements, of course, do not come without issues in terms of operation and maintenance as well of hydraulic machinery particularly. So we are experiencing premature aging as well as safe operations due to increased vibrations and fluctuations of pressure. That leads, of course, to increasing OPEX costs, failure, as well as lower response of machines, and also environmental concern. With a focus on the premature aging and especially risk of premature failing, of mechanical components, the sector is today developing new strategies. For understanding how to better steer potentially in an optimal way operation, how to develop new monitoring strategies, as well as can we move towards a predictive maintenance approach. And that, of course, also calls for novel technologies as well as design and materials. When it comes to premature aging and failure, one of the main topic is what do we know actually about fatigue-induced damage in hydraulic machinery? So what's fatigue? Fatigue is the deterioration of material properties, structural properties due to damage because of fluctuating stresses. In turbines, we often have such a condition because we often have off-design operation that leads to fluctuations coming from the hydraulic loading, and also transient operations such as startup and stop that, of course, impact and increase the steady loading as in transient operation we have to pass through unsteadiness operation of machines and so overflow. We have cracks in hydraulic runner. Even the best welding condition and best properties of manufacturer still held micro cracks in the structure because of manufacturing, because of the welding and material defect. And overall, we also have a quite heavy loading, hydraulic loading, that is translated into structural loading. And this long-term operation under high loading, of course, also lead to micro cracks formation. Issue is that those crack propagates under those cyclic and steady loading, and that can lead to failure. What do we know about how the forecast and modeling of fatigue? Do we know today how to properly forecast and track how to cracks propagate? To answer to this question, we mainly have to understand what are the dynamics and analysis that leads to such a forecast. In particular, how a crack propagates and how to forecast also so the deformation of a runner itself during operation. We need first to know, in terms of structural analysis, what are the loading conditions of the machine. So what are the hydraulic loading through the different operating conditions. So not only, of course, steady state, but also during those transients that leads to stresses. And we want to know what are those maximum stresses, are those compatible with the structural properties of the runner. But we also need to know the model analysis response. So what are the both modes and natural frequencies that also, of course, are related to damping and added mass and mode shapes. So what is a fluid structure interaction actually behind the deformation of the runner? There are some approach today that leads so to an analytical understanding of both the modal response as well as the structural loading of runners. But the issue is that this knowledge today is limited to selected studies, and there is a lack in understanding how both structural loading and natural response are through the operating range, in particularly during the transient condition. So is to fill these gaps that we are currently addressing quite important research effort to try to understand to those problematics and give so a research a scientific answer to such research questions. How do we do that? We leverage our experimental capabilities. So here you have one of our test rig where we test so reduced scale model testing that you can see here. Let me put the laser, it will be easier. Here, that's so the model test that we want to study, and in particular, so you will see later we perform measurements directly on the runner during transient condition to measure the stress and of course also the hydraulic properties of a flow. And the flow so come from here. We have all the energy of the flow, which is given by the feeding pumps that allows us so to drive the flow both in turbine and pumping mode. We try to keep similarity laws as close as possible, so to IC standards also for transient conditions, so to respect both Reynolds above 5 million, Freud similarity as well as the Thomas similarities when we assess the cavitation performance. This is our telemetry system and the equipment that we use to perform such a study. So the telemetry system allows us to do onboard measurements of both strain through strain gauges on the blades. Here, for instance, you have an example of one of the equipment that we used, and also pressure measurements on the runner. So the telemetry system is the same, and different sensors can be exploited. Of course, we want still to track what happens to the steady part of the machines. So we namely have several sensors in the machines in the static part, at the guide vanes, surface, in the vanilless gap, and into the draft tube. Here is not represented, but we have some also in the upstream pipes to eventually study any upstream wave that could affect the pressure fluctuations. The selection of how we put the stress is not only to measure the stress itself, but also to understand what are the stress gradient and also what are the proportion between the tensile and the bending stresses. As we know, when we have a pure crack propagation, only the tensile stress today in crack propagation methods are accounted for, while when we use stress life methods, so based on a Wöhler curve, typically, in that case, both tensile stresses and bending stress are taken into account. So we want to understand how those different way of exciting the material actually impact then on the counting of the stresses and so on the overall on the estimation of the lifetime. How does a transient sequence that we test looks like? Here you have an example for a startup sequence, both for a synchronous machine, so where the grid synchronization has to happen, so the operation through a speed no load is a characteristic of such a transient. So you have a fast acceleration of around your speed, then speed no load, all these at a rather low guide vane opening, and then you accelerate the flow up to a nominal condition. And then we also tested what if we have a full-size frequency converter, and so we are able to accelerate linearly without passing through the speed no text of a frequency converter. This study, some of you might have met Martin Sedu while he was with me at NTNU a few years ago. This was one of the main results of his thesis in studying the stresses and the damage. And one of the main conclusions was that if we are able to use a variable speed converter, we are able actually to decrease the lifetime, the fatigue, so to increase the lifetime of a machine and to decrease of up to 15 times fatigue-induced damage reduction in a single startup time. So here you have a stress measurements through in this case, 25 seconds equivalent in model scale. Of course, in the prototype that would be longer, or in 8 seconds if we can use a fast full-size frequency converter. You might notice that here we have quite high oscillations in terms of amplitude of the stress fluctuations that we do not have in any other operation here, even though the overall stress is lower, of course, for the linear startup. And we can also see that such a stress amplitude converge at what happens in the cone and is linked this, we observe that is linked to a vortex rho. So we want to know more with this. So we performed both high-speed camera acquisition as well as particle image velocimetry with our equipment. And here I want to just show you a video showing what happens. So the video is not from the beginning, it's specifically from this red window. So we want to see what happens when we have such a high fluctuation of stresses, which is not recorded otherwise in synchronization. And you see the appearance. We decrease the Thoma number because we wanted to visualize this with high speed. So you could see this double helix, double vortex rope, but then break down into a single vorticities. And then you have the passing through the first partial load, then full load, and then best efficiency point. What does the PIV says? So with the PIV, what we notice, so we have the beginning where we have no gravitation and the flow accelerates. Then we can see the creation of these double vorticities where only one vortex cavitates. Then we have the double vortex cavitation, and then a vortex collapse, a uniform flow, and then the axiomatic vortex rope. So we notice that this fluctuation here is related to when it happens, the double cavitation, the double vortex cavitation, and when we have a collapse of this in the single vortex. We were quite limited with this PIV because it's not fully time resolved. In reality, this is a 10 Hertz classical PIV system. So we could not push forward with our measurements. So we thought, why don't we perform a CFD to see if we are able to capture such a dynamic? So as a solver, we use coupled numerics. This is a software developed at the high, that's in German. Anyway, technical university in Lausanne. So it's a collaboration that we did with Ernesto Casastelli. Some of you know him from University of Lausanne. They developed such a software, and so in this collaboration we use it in order to predict the hydrodynamics of the flow during the startup. It has the advantages of being a deformable mesh, so you don't need to have a remeshing during the transient, and offer also a fast fluid structure interaction approach. We used our measurement to impose the boundary condition, and we were able to simulate a very close to the almost zero. We went close to a 2 degrees opening of guide vanes, so without remeshing, but increase decrease significantly so the computational cost. As a turbulence model, we tried the two. At first, that is known in literature to be best for speed no load and capture the anisotropy of stress Reynolds, however, which is this one. However, you can see here you have the PIV, here you have the results of a simulation with this turbulence model. However, you see here that dynamics of a double vorticity is not well captured. So we also use the other turbulence model, which is a little bit more heavy, however, that solves individually the Reynolds stress equation. And with this, you can see the result. We could perfectly capture the double cavitation vortex as well as the full background breakdown of the vortex. Here you have more deeply the understanding of what is happening. So we have clearly the multiple vorticities that develops during the startup of a sequence, and they originate at the blades. So you can also see the development of the interblade vorticities, and it is these dynamics, and of course this is still an ongoing study. So the next step would be to fully correlate the dynamics of such interblade vorticities and the breakdown of a double vorticity into one single per section vortex rope with the dynamic of stress. But already offers a very good understanding of what happens in the runner, where the vorticity form, where the vortex collapse, and how that justify an increase of stress fluctuations that leads to higher fatigue in the runner. I also have a video, but I was not able to put it in the presentation, so maybe eventually I can show you to you later. So I want us to quickly conclude with the validation of this. So it's not only a matter of comparing the velocity field. We verified that also in terms of pressure fluctuation. So in this case, we have a spectrogram of the pressure in numerical simulation and experiments at the leading edge, into the draft tube, and at the trailing edge, to be sure that we were capturing correctly the physics of the flow. And so that's we could validate it. And so as a conclusion of the talk, and I had then a slide on the outlook, as I said, that those are ongoing fresh studies. So definitely flexibility is impacting the lifetime. With a study on how to steer differently transient operation, in particular startup, we can reduce the damage, but still we need to understand, in order to understand how to optimally steer such transient operation, we need to understand what is the transient vortex dynamics and how that impacts on stress amplitude. So in this sense, we have ongoing research efforts to try to understand this underlying fluid dynamics, fluid structure interaction dynamics, as well as what is the impact of multiphase flow, as we saw that when it cavitates, the fluctuations of stress significantly increase in amplitude. So we currently have such a research effort with what I show you, our work performed that are published or publication is under review, and we currently have further research effort on this. So those are the 4 PhD students that with a different angle tackle the problem. You have Sarah, elucidating the transient vortex dynamics, so building directly upon the results that I show you right now. We have both Eli and Jonas, that are looking more at the fluid structure interaction and transient impact on added mass and hydrodynamic damping. Those are for startup mainly, but we are also interested to know how such a dynamics is affected by transient operation when we change mode. So when we passed from turbine to pumping mode and vice versa in reversible pump turbine. So for this, Nathan is currently investigating the flow phenomenon and the fluid structure interaction during such mode transition. You can see here some first result. This is the evolution of it's the spectrogram of the pressure fluctuation in the Van Allen gap when we change mode from turbine to pump in 50 seconds. And in particular, we are interested to know when we are in pump dissipation mode, either to turbine or to pump, what is the effect of the transient dynamics on rotor-stator interaction and rotating stall. Well, so that's it. I thank you very much for your attention. Here you have a few references of some work that are already published on those topics on fatigue during transient operation, and happy to take your question.